Hello, am I audible? Okay. Okay, so let's begin. So welcome to week 6 of these problem solving sessions on the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. My name is Saleh Khan and I'm a PhD student at IIT Delhi, and I will be conducting these sessions on Mondays. So I will again, usually as I do usually, I will begin with a summary of the content that was taught in the week. And this time the following topics were taught. We started with voltage and current source inverters, and then we moved on to pulse width modulated inverters, and then talked about multi-level inverters, and finally Z source inverter. So here you can see a simple basic principle of the voltage source inverter. So we will have a DC voltage source which will be provide a constant DC voltage, and then we will have usually multiple half bridge legs. So half bridge means we have two switches connected in this fashion, where they are connected to the same. They're connected. One is connected to the positive bus, and another one is connected to the first one, and then the second one has one of its terminals connected to the negative bus. And we take the output from the midpoint of the switches. So this is a half bridge configuration. In multi-level cases, this can be different, but this is the commonly used configuration. And the rule here is that the switches S1 and S2, they cannot both be on at the same time. Because if they are both on, then the input voltage will be shorted through the devices. So the devices will have high currents and it will damage the devices as well as the source. So now we can see if we want to achieve a AC voltage at the output, because these are inverters, we can have two options here based on how these switches are operated. One option is that we turn on S1 and we turn off S2. In that case, the point A will be connected to the point P. So we will get full DC voltage across VAN. So across the ground and the output terminal, we will get VDC. The other option is that we turn off S1 but we turn on S2. In that case, A will be directly connected to N, so there will be no voltage across AN. So the voltage across AN will be 0. So in this way, we can get these two voltages, VDC and 0, across VAN. And by extending this concept to multiple half bridges or other scenarios, we can get the desired AC voltages. So this was voltage source inverters. Now a current source inverter will be quite similar, except instead of a voltage as the source, we now have a current source. So the current source will provide a constant DC current, IDC. And usually this can be a voltage source in series with an inductor, a high inductance, which will not allow the current value to change. So that we can consider as a current source. But here the rule that we have is that both the switches S1 and S2 cannot both be off at the same time. So they can both be on. If they are both on, then the IDC current will flow through them. So there is no issue of damaging. But if they are both off, and let's say we don't have any other legs for the inverter, then the IDC current will not find a path to flow. And since we are saying it is a current source, this current has to flow somewhere. So if we don't allow a path to it, there will be some damage, because if it is an inductor and suddenly we are opening both the switches, so it was carrying some current and then suddenly it does not find a path, so the current will go to 0, and because of the high dVdt, there will be voltages induced in the inductor, and that those voltages will damage the components. So in for a current source inverter, the both switches cannot be off at the same time. So now if let's say S1 is on and S2 is off, then the current IDC will flow through point A. It will flow through the output. So we will get IDC current at the output. If both are on, then the current will just flow through S1 and S2 and back to the source. It will not flow through the load, so that we get zero load current at the output. So this is how current source inverters work, and the difference between voltage source and current source, I think, is obvious. Now there are some aspects of functionality also there that changed. Like I said, that in voltage source both switches cannot be on at the same time, but in current source both cannot be off at the same time. But in the next slides and in the lectures that we'll follow, we will mostly talk about current voltage source inverters. So let's see how a single phase voltage source inverter works. So now we have two half bridges. Instead of just having one half bridge, we now have two half bridges, and the load is connected between the midpoints of these two half bridges. So the simplest way to get an AC across the load AB is to first, in the first half cycle, turn on the switches S1 and S2. So when S1 and S2 are on, the point A will be connected to P and B will be connected to N. So we will get plus VDC at the output. So the output VAB will be plus VDC. And then in the next half cycle, we will turn on S3 and S4. And we will turn off the previous two switches. So by turning on S3 and S4, the point A is now connected to the negative terminal and point B is connected to the positive terminal. So we get negative voltage across the load. So in this way, we'll get an AC voltage at the output, which is a square wave. This is the simplest way to do it. And depending on how the load is, whether it's a resistive load or inductive load or RLC load, we will get some kind of a current. And so we can say that we can get this kind of a current as well that I've shown in blue or the fundamental of the load current can look like something like this. And you can see that it's a lagging current, so kind of an RL load or some kind of very high inductance load. So if you see these waveforms, then you will understand that the switches that we are using, they have to be voltage unidirectional and current bidirectional. So what do I mean by that? I mean that the voltage that they are blocking is always positive. So for example, when S1 is off and S4 is on, then this point A is connected to N point. So the voltage across S1 is the VDC voltage, the positive VDC voltage that it has to block. So if you see for all these switches, they only have to block the positive VDC voltage. But the current that they are carrying, it can be positive as well as negative. For example, here we see that S1 and S2 are on, but the current is negative. Because of the lagging current, initially the current is negative, so it is flowing from B to A. So it will be a negative current. And then the current becomes positive. So, and later on again for S3 and S4, you will see that the current can be both positive as well as negative. So for VSI, the switches have to be voltage unidirectional and current bidirectional. For CSI, it will be different, but so focusing on VSI right now, so this is the switch requirement. So now we can come to three-phase VSIs. So again, we can use the way we did it in the previous for single-phase operation, but now we will have three half bridges that are connected to the same DC voltage or DC bus, and the three outputs are taken from the three midpoints of the half bridges, and then we can have a star connected load or a delta connected load. Here I've shown a star or Y connected load. And so now we have the simplest option, or the one that we had seen for single phase. Now we can apply to a three phase. This is called a 180-degree conduction. So simply S1 is on for half the cycle, or pi angles, or 180 degrees, and then S4 is on for the next half cycle. And for the other legs, we do the same thing, but we delay them by 120 degrees for the B leg and 240 degrees for the C leg. That is how we get three-phase balanced voltages. So if you see the voltage VAN, when S1 is on for the first half cycle, we will get plus VDC, and then when S4 is on, we will get 0. So the trace I've shown in black, that is actually the VAN voltage. Similarly, VBN will be same, but shifted by 120 degrees, and VCN will be shifted again by 240 degrees or 120 degree from the VBN voltage. So then we can find the line voltage between the three lines. So I have shown VAB here, and VAB we can just find from subtracting VAN and VBN. So you see that for the first 120 degrees, we will get VDC at the output, and then we will get 0 at the output because VAN and VBN are both positive VDC, and then we will get negative voltage. So the output will look like a quasi square wave, and if you find the RMS of the fundamental of this waveform, you will get it is 0.78 VDC. So this was about 180-degree conduction. So another type of conduction that we can have is called 120-degree conduction. So here, instead of the switch being on for 180 degrees, the switches are only on for 120 degrees, or 1/3 of the full cycle instead of 1/2. So here we first turn on S1 for 120 degrees, then after half the cycle, or after 180 degrees, we'll turn on S4, and in between for the A leg, both the switches will be off. And for the other legs, we'll do the same thing, just shifted by 120 degrees. So if you see this, now let's try to find out the line voltage. So when S1 and so in the first 0 to 60 degree operation, we have S1 and S6 are on. So in leg A, S1 is on, and in leg B, S6 is on. So we will get VDC across AB. So that is understood because A will be connected to point P and B will be connected to point N. So we will get VDC across VAB. So now in the next 60-degree operation, S1 is on, but in the phase B, there is no switch that is on. So this point B is just floating. So since it does not have since S3 and S6 are both off, there is no path for the current to flow. So the load will not have it, B phase will not have any current. And we are assuming that it's a resistive load, or mostly resistive load, so that the current also dies down with the voltage. So we can see that S1 and S2 are on, so we will get the VDC voltage across AC. And if we are assuming that the load is balanced, so all the loads have same impedance, then half the voltage will be across VAO and the other half will be across VOC. Right? So point B will be just connected to the O point because there is no current here. So the voltage across AB will be VDC by 2. So I hope you can understand this. If you're not understanding, you can just ask in the chat that the voltage across VAB for the second 60-degree interval, it will be VDC by 2, because the voltage across VAC will be VDC, and the B terminal there is no current between B and O, so the potential at P is the same as potential at O, and the potential at VAO will be half of the VDC. So in this way, you can find out the full line voltage, and you will see if you do the Fourier analysis that the fundamental is 0.67 VDC. So this is less than 180 degree conduction, where we had gotten 0.78 VDC. So 120 degree conduction is a different method here. The advantage is that the device is conducting for less amount of time. But the drawback is that we get less voltage at the output. So this was the basic three-phase and single-phase voltage source inverters. Now we come to pulse width modulation. So the first question is, why do we use pulse width modulation? So, and the answer is that we want to reduce the lower order harmonics in the load voltage and current waveforms, mainly current waveforms. So how do we do this? So we can start with the single phase inverter, and let's see with just one pulse. So the previous method that we saw, that we had for half the cycle S1 and S2 are on, and then the next half S3 and S4 are on. So we get the pulse width is from 0 to T by 2. So 180 degrees is the pulse width. Now if we can reduce this pulse width by turning on different switches. So after S1 and S2, we can turn on S4 and S2, and the other switches are off. And when S4 and S2 are on, you can see that the voltage across the load will be 0. So we get 0 voltage across the load. Then again we turn on S3 and S4 to get negative voltage, and then we turn on S1 and S3 to again get 0 voltage. So what we are doing here is we are reducing the pulse width. So instead of 180 degree, now we can have what I've shown here is 2D. So now the pulse width is variable. It can be very low and to maximum of 180 degrees. So what advantage does this give us? So if you do so instead of a square wave, we now have a quasi square wave at the output. If you do the Fourier analysis of this, you will find that so here I've shown in this figure the peak value of different harmonics normalized to the peak value of the fundamental. So if you see, as the pulse width we are increasing from 0 to pi, the fundamental will also increase. And you can understand that if the pulse width is very small, then we have a very small fundamental at the output. And as we increase the pulse width, we will get closer to 180 degree operation. And at pi, when 2D is equal to pi, then we get the full fundamental at the output. Now this was about the fundamental, but what about the other harmonics? So the interesting thing here is that depending on the angle, or 2D, the pulse width, the amplitude of different harmonics changes. So for example, the third harmonic, which is n equal to 3, if 2D is equal to 120 degrees or 2 pi by 3, then the third harmonic will be 0. Similarly, for the fifth harmonic, there will be certain points for 2D where the fifth harmonic will also be 0. And similarly for other harmonics. So the point here is, by varying the pulse width, we can eliminate some harmonics. And this was just with one pulse. If we have multiple pulses, then we can eliminate or reduce multiple harmonics. And in general, by having a very high switching frequency or very high number of pulses, our harmonics will be more and more reduced. The lower order harmonics will be reduced, but the higher order harmonics may be introduced. But with inductive loads or capacitive loads in parallel, the advantage is that the higher order harmonics are very easy to filter out, because the impedance of the inductor at high frequencies is very high, because the impedance of the inductor is omega times L, where omega is the frequency. So for very high frequencies or higher order harmonics, in that case, our filtering becomes easier. So this is why we use pulse width modulation. So the first option is to have a single pulse, and that can be generated in this way. So we have a carrier, VC is the carrier. The carrier will be a triangular waveform, and then we have a reference waveform. And when the reference intersects the carrier, at that point we will turn on the switch, and when it again intersects, we will turn off the switch. So we will get one pulse in this case. To have multiple pulses, then we will have to increase the frequency of the carrier. So if we increase the frequency of the carrier and we still have a constant reference, we will get multiple pulses, and the pulses will have equal width and will be spaced also equally. So in multiple PWM, we will get advantages of we can reduce the harmonics further, lower order harmonics. And finally, we can have a sinusoidal PWM where the reference is also varying. So instead of having a constant reference, it is varying sinusoidally. So our pulse width will also vary sinusoidally, and the space between the different pulses will also change. So in this case, we will get even better harmonic performance. So the modulation index is the ratio of the amplitude of the reference waveform and the carrier waveform. And by increasing or reducing the modulation index, we will get lower or higher voltage at the output. So by having more pulses, the lower order harmonics will be reduced further, but the switching losses will increase because of if we want multiple pulses, we'll have to switch on and off the devices much faster. So we will get more switching losses. So this was an introduction to the pulse width modulation. Now we can come to the other topic, which is multi-level inverters. So on the left, this is the type of inverter we have seen in the previous slides. It is the two-level inverter, and the two levels are 0 to VDC. So we can only go to 0 to VDC. When the top switch is on, we will get VDC across VAN, and when the bottom switch is on, we will get 0. So these are two levels. Now, in order to get a three-level inverter, so this is basically just a schematic to understand how it will work. So this is not the actual circuit. So now we will have the single input. We will have two capacitors of equal value, so that we will get VDC by 2 across each of them. And then we will have another switch connected between the capacitors and the switches, the half bridge switches. So here we can get three levels across VAN. When the top switch is on, we will get VDC across VAN. When the bottom switch is on, we will get 0. Now when the midpoint switch is on, we will get basically VDC by 2 at the output across VAN. So here we have three levels at the output, 0, VDC and VDC by 2. So now how to realize this kind of a circuit? So that is the question, and there we have multiple answers. So one option, so before going to that, I just want to talk about why we are using multi-level inverters. So we have seen in the case of two-level inverter, the output voltage looks something like this. The square wave or the quasi-square wave that I have shown. But the fundamental or the voltage that we want we want the voltage to ideally look like a sine wave. So by having a multi-level inverter where the levels are smaller compared to the two-level inverter, we can switch in such a manner that we can have a very closer approximation to the sine wave. So if the approximation is closer, then the error between what we want and what we actually get will be also less. So you will actually see that we will get lower harmonics in case of multi-level inverters. So the advantage of multi-level inverters is that we get lower harmonics, Also, the switch stress is reduced. So in the first case for two-level inverter, we had the full VDC across the voltage. The devices have to block full VDC. But for multi-level inverters, they have to block less voltage. So like 3 level, they can be VDC by 2, they have to block. And we also get reduced DVTT and EMI. So because the switches are switching for lower voltage, so instead of VDC, the change in the voltage is now VDC by 2. So the dV by dVdt, if you see, because the dV is smaller, dV by dt is also smaller, so the magnetic radiation is also smaller. But the drawbacks of the multi-level inverters you can understand is that we now require a more number of devices and capacitors, so the component count is increased. So it may be more costly as well. That's not necessary, but most of it may be more costly, and it will require more. It may require more space, and in general, the complexity is also increased because now we have to control more switches. The simple method of control will not work. You will have to require some more complex methods of controlling these converters. So now we can talk about the different kinds of multi-level inverters. So the first one is a diode clamped converter, multi-level converter. So now here I've shown how the diode clamp will have for a 3-level case. For a higher level case, there will be more devices. But for a 3-level case, this is how it will look. So we have 4 switches. They are connected across in the same leg. And then we have 2 diodes. They are connected between the midpoint of the capacitors and between 2 different devices, if you can see in the figure. So now if we require VDC across the output is I'm taking as the point A and the negative point of the input endpoint. So across VA, and if we want VDC at the output, we will turn on S1 and S2. So if we turn on S1 and S2, then the point A will be connected to the positive terminal, so we will get VDC across VAN. Now let me first come to the 0 point. If we want 0 at the output, we will turn on S3 and S4. So that's quite simple to understand. We will get 0 at the output. Now if we want VDC by 2, we will turn on S2 and S3. So the middle switches, we will turn on both of them. And depending on how the current direction is, different devices will conduct in this case. So if the current direction is positive, so it is out of the A terminal, then the current will flow from D1, from the midpoint of the capacitors through D1 and S2, it will flow to the load. So even though S3 is on, the current will not flow through S3 in that case. So that is for positive current. If the current is negative, then it will flow through S3 and then through diode D2 towards the midpoint. And again, since the point A is connected to the midpoint, we will get VDC by 2 at the output in both cases, the positive current as well as the negative current. So we'll have different devices that are conducting depending on the current direction. But in both cases, the point A will be connected to the midpoint of the capacitor. So we'll get VDC by 2 at the output. So this is how the diode clamped multi-level converter works. And for higher levels, we will just have to add more devices, and then you can figure out which device will conduct in what case. So this was diode clamped. The next type of multi-level converter is a flying capacitor converter. So here again we have 4 switches in each phase leg. Then we have additional capacitor which is connected between 2 switches as you can see in the figure. And the capacitors are maintained to have a voltage of VDC by 2 across them. So this we have to see the modulation, how we will switch. So it has to follow this condition that the capacitor voltage has to be VDC by 2. And then you can understand that if we Now, if we want VDC at the output, which is AN, we will turn on S1 and S2. By turning on S1 and S2, the point A will be connected to the point B. And if we want 0, we will turn on S3 and S4. And now if we want VDC by 2, we have two options to get VDC by 2. One option is we will turn on S1 and S3. So if you see, I will start from point A. I will go through S3 and then through the capacitor to S1. And if you see the voltage between point A and point N, it is VDC minus VDC by 2. So we'll get VDC by 2. Similarly, if I turn on S2 and S4, I will get the VDC by 2 capacitor at the output. So I have two options to get VDC by 2. And that is something that is used in the modulation of this converter to balance these capacitor voltages. So this is how a flying capacitor works. So both have their advantages and disadvantages. One of the advantages for the flying capacitor is that we don't require two additional diodes, but we require additional capacitors. So the size may be larger in this case because the capacitor take more size. But both basically have different applications and different advantages. So the third multi-level inverter that was taught was cascaded edge bridge, but since that is relatively simple, I will not consider that here. So finally, I will talk about the Z source inverter. So there are different types of Z source inverters and they are used in various applications. So when we want to talk about in an inverter application from DC to AC, so I will choose one of the types of Z source inverter and just try to tell you the principle of working of this inverter. So here we have the simple VSI, but between the source and the devices we have an impedance network. And since this impedance network is connected at the input, that is why it is called an impedance source inverter or a Z source inverter, where Z is the impedance. So this kind of an inverter will provide us with some additional functionality compared to the VSI or CSI. And I will here focus on the VSI based Z source inverter, which I have shown in this figure. So there can be now different states of operation. So I had mentioned previously that for the VSI, we cannot have both devices in a half bridge turned on because then we will get a short circuit of the input. But for the Z source inverter, because we have the impedance network between the source and the half bridges, even if we turn on the half bridge, we will not get a short. So it is possible to turn on these two devices at the same time. So that is called a shoot through state. For the normal state, where we don't have a shoot through, we can analyze or we can draw an equivalent circuit of this Z source inverter, which I have shown here. In the normal state, we will have some current that is flowing through the load, which is I current, and then we will get a circuit like this. So this normal state, it will be operating for some time t1 in t1 out of the switching cycle, the full switching cycle t. For some time t1, we will operate it in the normal state. And if you see in the normal state, if we want to see the voltage across the inductors of the impedance network, and assuming that the two inductors have the same value, they will also have the same voltage because the impedance network is symmetric. Similarly, the capacitors too, if they have the same value, they will have the same voltage as well. So if we try to find out VL, which is the voltage across the inductor, we will see from a KVL equation that it is VDC minus VC. And if we want to find VI is basically the voltage at the input of the three half bridges. If we want to find VI, we can see that it is VC minus VL. And VL we can have from the previous equation that VL is equal to VDC minus VC. And if we substitute here, we will get that VI is equal to 2 VC minus VDC, where VC is the voltage of the capacitors. So this was in normal state. So normal state means we don't have a shoot-through state. But for a shoot-through state where any of the half bridge, both switches of the half bridge are on. So in that case, uh, there will be no load current, or the load, all the current will flow through the switches. Okay, so the voltage at the input of the bridge will be zero, right? In that case, the capacitors and inductors, they will just conduct through this loop, and there will be no current from the input source as well. So in that case, if we want to now find out what is the voltage across the inductor, so VL will be equal to VC. So if you see, for example, this loop, VL will be equal to VC. And VI in this case will be 0 because it is a shoot-through state. So the input to the half bridges is shorted, it is 0. So this is the two states that we have. So we will, for if we have a time period of t seconds, capital T seconds, for a portion of that time, t1, we will have a normal state, and for another portion of the time, we will have a short shoot-through state for t0 time. And if we add these two, t0 plus t1, we will get the full time t. So now we can use the volt-second balance view across for this inductor voltage equations. So if we do the volt-second balance, we will find that VC is given by this equation, that VC is equal to T1 divided by T0 plus T1 times VDC. And if we want to find the peak of the VI voltage, so the peak of the VI voltage will be in the normal state. So because in the shoot-through state, VI is equal to 0. So the peak of the VI will be in the normal state, which is given by 2 VC minus VDC. And if we substitute the value of VDC from the volt-second balance equation, we will get this equation, where we have VI is equal to T divided by T1 minus T0 into VDC. So this factor T divided by T1 minus T0, this is called the boost factor, B, because this factor is greater than or equal to 1. Because if you see T1 minus T0 will always be less than T. So T is greater than T1 minus T0. So this whole factor is greater than 1. So the VI voltage is the VDC voltage times some boosting factor. So basically it means that if we now want to find out the output AC voltage, which is given by modulation index times VI by 2, and we substitute the value of VI from the previous case, we will get MB times VDC by 2. So the output voltage we can have greater than the input DC voltage, because for the VSI we can only have buck operation, but in case of Z source inverter we can have both buck as well as boost operations. It's a buck boost inverter. So that is the advantage of having a Z source inverter, and that is why we use these kinds of inverters. So now let us come to the problem solving, the problems that we have to solve in this case. So now the first problem is that we have a single phase half bridge inverter which is feeding power to a load resistance of 10 ohm. the DC input to the inverter is 400 volts. So the question is asking to determine the power that is delivered to the load. So let us first see how a single phase half bridge inverter looks like. So we have one half bridge, and at the input we have two capacitors, and the load is connected between the half bridge midpoint and the capacitor midpoint. So the capacitors are equal in value, so they will both have VDC by 2. And when S1 is on and S2 is off, we get VDC by 2 across the load. And when S2 is on and S1 is off, we get minus VDC by 2 across the load, VAO. So in this way, we will get VDC by 2 only at the load. So for a full bridge inverter, we will get VDC, but for a half bridge, we will only get VDC by 2. Even though, so this requires less switches, but we get only half the voltage at the output. So, and if we have a resistive load, the current waveform will look like the voltage waveform. It will just be voltage divided by the resistance. So now we are told that the VDC voltage is 400 volts, so VAO will be 200 volts. The peak of the VAO will be 200 volts. And the load current will be the voltage divided by the resistance, which is 20 amperes. So if we want to find the power, which is voltage times current, we will get 200 into 20, which is 4000 watt. So the answer to this question is 4000 watt, the power that is delivered to the load. So the second question is asking the conduction time of the diodes if SCRs are fired at 0 and T by 2 in a single phase half bridge inverter with R load. So the options are 0, T by 2, 2 by T, or the question is saying whether there is insufficient data. So let's first see what the circuit looks like. So here the switch that we previously I was using a generic switch. So now here we are told that they are SCRs and diodes, because the switch has to have bidirectional current capability. So that is why we have a SCR and then anti-parallel diode. The anti-parallel diode will carry the negative current. So the question is saying that the SCRs are triggered from 0 and then T by 2. The question is asking what will be the conduction time of the diodes. But in this case, since the load is only resistive, the current will always be in the direction of the voltage. So there will never be a negative current when the voltage is positive. So there will always be positive current. And when the voltage is negative, the current will also be negative. So, and that will be handled by the SCR itself. So there is no, for the resistive load, the diodes will not conduct at all. So the answer to this question is that the conduction time of the diodes is 0, because for a resistive load, the diodes will never conduct. Because if I go back, so for example here, for a resistive load, the current is always in phase with the voltage. So when S1 is on, or the first thyristor is on, the current will be in this direction from A to O. And when S2 is on, the current will be from O to A in the negative direction. So, but it will be handled by S2 SCR. So the diodes will never conduct for a resistive load. So the answer to this question is 0. So this is the third question. So before we solve the third question, we can have a short break. And in the meanwhile, you can try to answer this question. So it is a single phase half bridge inverter again. So with resistive load, you have seen the circuit. So now the values are given. So you are asked to find the average value of the supply current. So we will have a short break until, so in 9 minutes we will resume. So at 7 p.m. we will resume. Okay, you can try to solve this question in that time, in the meantime. Okay, so let us continue. So has anybody tried solving this question? So if anybody has tried, you can post your answers in the chat. Okay, in the meantime, I'll just, again, this is the half bridge inverter configuration, the circuit. So the question is asking about us about the source current. So the way we can do it is just we can find the power that is given to the load, and then the same power will be supplied by the source, and we know the source voltage. We can get the source current. So somebody has raised their hand. So does anyone have a question? Okay, so I'll just go ahead. So to find the power that is given to the load, we can just multiply VAO by IO. So VAO in this case will be VDC by 2, and the current is VDC by 2 divided by the resistance. So we will get a power of 240 watts. So that is the power that is given to the load, and it must be supplied by the source. And we are assuming that there are no losses taking place, or the losses are very small, so that they are negligible compared to the load power. So then we can find that the supply current will be the power divided by the DC voltage. So we will get 240 divided by 48. So the supply current is 5 amperes. So the answer to this question is A, 5 amperes. So the fourth question is asking that what will be the shape of the output current waveform for a single phase full bridge inverter on an RL load. And the options are sine wave, square wave, triangular wave, or constant DC. So what do you think? Can anyone You can post your answers, what you think is the answer, in the chat. So this is a full bridge inverter. So we have seen how the voltage waveforms look like. So now we have a RL load instead of a resistive load. So what do you think the current waveform will look like? Okay, so for the resistive load, we have a purely resistive load. The current waveform will follow the voltage waveform. And since the voltage is square wave, the current will also be a square wave. So this is for a purely resistive load. Now for a purely inductive load, when we apply a positive voltage across the load, the load current will rise. So if it was negative at the start, it will continue to rise and then become positive. And then when we apply a negative voltage across the load current will fall. So for a purely inductive load, the load current will be triangular. Now an RL load is somewhere in the middle. So it will have, so if the resistance is very high, it will be closer to the square wave. If the inductance is very high, it will be closer to the triangular wave. But we are assuming that if the question is asking about the RL load, the inductance should be significant, so this kind of a current, it is more closer to a triangular current than a square current or a sinusoidal current. So the answer to this question is a triangular waveform. So the output current for a single phase inverter with an RL load looks like a triangular waveform. So in a three-phase inverter, the next question is saying that in a three-phase bridge inverter, each step consists of, the options are 30 degree, 60 degree, 90 degree, and will depend on the value of the firing angle. So for example, let us consider the 180 degree operation. In 180 degree operation, if you see that for each 60 degree interval, a different combination of switches is on. So for the first 60 degree, if we see S1, S6, and S5 is on. For the next 60 degree, S5 has been turned on and S2 is on. So every 60 degrees, some switching changes. So if you see the load line current and the phase current will show that phase voltage will show that it has different values for every 60 degree. So the load has phase voltage that has 6 steps in one cycle. So that is why it is called a 6-step inverter. So the answer to this question is that 60 degree, there are 6 steps with 60 degree in each step. The next question is asking about 180 degree mode of operation of the VSI. How many devices conduct at a time? So we just saw in the previous slide. So can anybody post what the answer is? Okay. So as we saw, there will be, for 180 degree conduction, there will be at least 3 switches, or exactly 3 switches that are on at one time. So for example, in the first 60 degree, S1, S6, and S5 is on, and in the next one, S1, S6, S2. Similarly for the other cases as well. But every instant, there will be 3 switches that are on. Out of the 6, 3 will be on. For 120 degree, on the other hand, there will only be 2 switches that are on. So for example, in the first case, first 160 degree interval, S1 and S6 are on. But in the leg C, there is no switch that is on. So for 120 degree operation, only 2 devices are on at one time. But the question was specifically asking about 180 degree mode. So the answer is D. 3 switches are on at one time. The next question is asking that we have a 3-phase inverter that is delivering power to a resistive load from a 450 volt DC source, and the load is star connected with 10 ohms per phase, we are asked to determine the load power, and we are told that it is 120-degree mode of operation. So let us see how the waveforms will look like in 120-degree mode of operation. So I've already mentioned how the switching is done. So for leg A, we will turn on the switch for 120 degrees, then we'll turn it off until the next cycle. And after 180 degrees, that is after half the cycle, we will turn on the other switch S4. And for other legs, we will do the same thing, but 120 degrees shifted. So, okay, let us try to find the load voltage, the phase voltage across the load, AO. So when S1, so in the first 60-degree interval, S1 and S6 are on. So the voltage across AB will be VDC. And since we are saying that the load is balanced, so half the voltage will be across VAO and other half will be across VOB. So VAO across VAO will get VDC by 2. Similarly, in the next cycle, S1 and S2 are on. So across VAC, we will get the full DC voltage, but across AO, we will get half of it. For the third interval, in the first leg, no switch is on. So basically, there will be no current through the load. So the voltage, if there is no current, then the voltage also will be 0. Since we are told that this is a resistive load, 10 ohms per phase. So this is how the phase voltage will look like. Now the current for a resistive load will look the same, but it will have a different value. So instead of VDC by 2, the peak will be VDC by 2R. It will be just voltage divided by the resistance. So the RMS of that voltage is, you can easily find out that it will be square root of 2 by 3 VDC by 2R square. 2 by 3 because it is on for 120 degree out of 180 degree. So you can just find out easily that the RMS of the load current is given by this equation. And once we have the RMS, we can then find the power that is delivered to the load. So I've used 3 I square R equation. Basically any equation you can find for the power and just plug in the corresponding values. So you will find that the power that is delivered to the load is 10.125 kilowatt. So the answer to this question is B, 10.125 or 13 kilowatt. So the 8th question is, so it is asking about a 3-phase inverter with a Y-connected load. It's an RL load, which is the values are given. Inverter frequency is 60 Hz and the DC input is 220 volts. Determine the line voltage RMS. So since it is not given which mode of conduction it is, and the general mode of conduction is 180 degrees, so I will assume that it is 180 degree mode of conduction. So in that case, the line voltage, we have seen how the waveform look like. It is shown here. It is a quasi-square wave. And now we are asked to find the RMS of this waveform. So again, just simple 2 by 3 of the VDC square and square root the whole thing. You will find the RMS, which is given by, in this case, 179.6 volts. So the answer to this question is 179.63 volts. So if anybody has any doubts, you can ask in the chat. So the 9th question is asking about pulse width modulation, how it is done. The question is saying that the output comparator output is high when, and the options are when the triangular wave has magnitude higher than the sinusoidal wave, or the sinusoidal wave has magnitude higher than the triangular wave, or C, the triangular wave has magnitude equal to the sinusoidal wave, or none of the above. So actually, the C cannot be the answer to this question because triangular wave equal to the sinusoidal wave is actually only for, it will only be for a brief interval of time, which is not possible to get a pulse width of that duration. So the answer is between A and B. And actually, it depends on what kind of a logic you use to turn on the devices. So the first option is that we will, so if we have a carrier or a triangular carrier, which I've shown here, and a sinusoidal reference. So one option is that the comparator output will be high when Vc is greater than Vr. So whenever the carrier value is higher than the reference value, so instantaneously, so because the carrier is going from 0 to Vc and then again to 0. So at some duration, the carrier is higher than the reference. At other duration, the carrier is less than the reference. So one option is that the comparator is output is high when the carrier is high greater than the reference. And then that comparator output will be given to some switch to turn it on or off. The other option is that the comparator output is high when the reference is higher than the carrier. So actually both of these options can be used depending on which switches are given the pulses. So we can have achieved the same output by, okay, so somebody is asking about the comparator. So in pulse width modulation, how this modulation is done actually. So we have a carrier waveform and a reference waveform. So these can be generated, whether we have a digital platform or an analog platform, we can generate these carriers and references. Now basically we want to, the objective of this carrier and reference to have these waveforms is that we want to know when to turn on which switch to get a sinusoidal PWM. So that is why we will have these two reference waveforms, one a carrier waveform and another a reference waveform. And we will give them to a comparator. So if we have an analog system, it can be an op-amp. Or if we have a digital system, it will like be an if-else condition or a comparator inside the digital system. And with both of these waveforms, the reference and the carrier will be input to this comparator. And then we can have different logics inside the comparator. One logic will be that when we see the carrier is greater than the reference, at that time we will turn on the switch. Or at that time the comparator output will be high, which will be given to the switch so that the switch will turn on. So that means, for example, in this case, if you see the cursor, in this duration, the carrier waveform is greater than the reference. So in this duration, we will get a output which is high. Afterwards, the carrier is now below the reference. So at that point, the output of the comparator will be low. So if that is given to a switch, the switch will be on in this duration, and then afterwards it will be off. So this is how the PWM works. We will have these carriers and references, and we will compare them, and we will get pulses that are given to the switches. So one option is the comparator output will be high when the carrier is greater than the reference. Another option is that the comparator will be high when reference is greater than the carrier. So these are inverse options, but both can be used, but we only have to understand which switch we are giving the pulses to. But the second logic, which is that the comparator is high when reference is greater than the carrier, that is used commonly. So that is what we will give the answer. And that is what was shown in the lectures, that the comparator output is high when the reference is greater than the carrier. So I hope that is understood, and if there is any further doubt, you can ask again in the chat. So the answer to this question is that the sinusoidal wave has magnitude higher than the triangular waves. The sinusoidal wave is the reference wave, and the triangular wave is the carrier wave. So the 10th question is asking that Several equidistant pulses per half cycle are used in which type of modulation technique? So the option are single pulse, multi-pulse, or sine pulse. So what do you think? And the fourth one is equidistant pulse. So what do you think is the answer? Can anybody guess the answer? So the question is asking about several, that means more than one, equidistant, that means the distance between the pulses is same, and we have several pulses per half cycle. So which type of modulation is this? Okay, so okay. So by equidistant, we mean that so if we have multiple pulses, one option is that after a given interval of time, so for example, after 10 milliseconds, we will have another pulse. And then after another 10 millisecond, we will have another pulse. So the time between the pulses is same, 10 millisecond. So that is equidistant. If, however, the time was different, so for example, we will have one pulse, then we will have no pulse for 5 millisecond, then another pulse, then we have no pulse for 10 milliseconds. So now the duration between the pulses is different. So that is not equidistant. Equidistant means the time between the pulses is same. And the options, so what we had studied is three options. So single pulse width modulation, multiple pulse width modulation, or sinusoidal pulse width modulation. In single PWM, we will only have one pulse per half cycle. So that our question was asking about several. So this is obviously not the answer. The other options are multiple and sinusoidal. In both cases, we will have multiple pulses per half cycle. Right? You can see that the reference is intersecting the carrier many times. So that is why we will have multiple pulses in each half cycle. But the question is also asking about equidistant. For sinusoidal PWM, if you see that the off times actually change. So for example, initially the off time is large, then it becomes small, and then again it becomes large. So the off times are different. So that is why in sinusoidal PWM they are not equidistant. The pulses are not placed equidistant. So that is why the answer to this question is multiple PWM, because in this case we have a constant line reference. That means the off times will also be the same. So I hope this is understood. The answer to this question is multiple pulse. And so that is all the questions that we had for today. So if anybody has any questions or any doubts, you can ask. Someone is asking whether we have any PDF which has every formula for all the topics we have in this course. I don't know if we have such a PDF because the course is being taught from different books. But we have, so the lecture slides are in different PDFs. You can download them, you can combine them if you want. So yeah, I don't know if there is only one PDF. Okay, so someone is asking about a recap. So I will just recap the summary of the week. So in this week, the topics that were taught were voltage and current source inverters, pulse width modulated inverters, multi-level inverters, and Z source inverter. So voltage source inverters, uh, so basically we want to achieve an AC voltage at the output and we have DC at the input. For VSIs or voltage source inverters, we have a DC voltage. So VDC, a constant DC voltage we have at the input, and we want to have AC at the output. So the basic configuration of the VSI has what is called a half bridge. Two switches that are connected together, and then they are connected across the input voltage. And the output is taken from the midpoint of this switch. And it can be connected, we can have one half bridge, can have two half bridge for a single phase, or three half bridges for three phase, or even more half bridges. So the rule for the VSI is that the two switches S1 and S2 in one half bridge, they cannot be on at the same time. Because if they are on, then our source will get shorted. So that will, if the source is stiff, that means it has constant voltage that does not change no matter how much current we draw, then we will draw a very large current because we are shorting the input side, and that large current will flow through the switches and they will get damaged. So that is why for a VSI, the two switches of the half bridge cannot be on at the same time. So now how we get the voltage at the output. So let me say I'm taking VAN as the output, where A is the midpoint of the switches and N is the negative point of the source. When S1 is on and S2 is off, we get VDC. And when S1 is off and S2 is on, we get 0. So in this way, we will get these two levels. And then we can, depending on where we connect this A point, we can have the AC voltages with positive as well as negative voltages. So this is the voltage source inverter. The current source is similar. Instead of voltage as the source or the input, we have a current or a DC current source. So it will provide a constant DC current value. And the rule here is that both of these half bridges cannot be off at the same time. Both of these switches in the half bridge cannot be off, because if they are off, then the current will not have any path to flow. And so basically, usually we have a voltage source plus an inductor, a very large inductor that makes the current source. But if now we are not providing a path for the inductor current, then the inductor current will go to 0 suddenly from some value. So dIdt will be high, so voltage will be high, voltage will be induced, that will damage the devices. So again, these are rules that we have to follow if in case otherwise the components will get damaged. So in this case, if the top switch is on and bottom is off, then we will get IDC at the output. Now, if both the devices are on, then the current will just circulate through the half bridge and it will come back to the source. So there will be no current to the load. So these are the two switching states for the half bridge CSI. So the difference between CSI and VSI is just the source input, and then there will be other corresponding differences in the switching and the loading, etc. So after this, we talked about how the VSIs and CSIs, the VSIs work for single phase and three phase operation. So here I've shown a single phase full bridge VSI and the simplest way to get AC, because I'm talking about simplest in the sense that 180-degree operation for this single phase is the simplest. Otherwise, for pulse width modulation, single pulse, multi-pulse, or sinusoidal pulse, that is more complex. The simplest way is just to have S1 and S2 turned on for half cycle, and for the next half cycle, S3 and S4 will be turned on. So we will get plus VDC for the first two half cycle and minus VDC for the next half cycle. So we got an AC voltage. So it's not a sinusoidal AC, it's a square wave AC. And then depending on what kind of a load we have, we will have some kind of a current. The current can be leading or lagging. So here I've shown a lagging current. And whenever we have a lagging current, so we will require the devices that are current bidirectional, because the current is both positive as well as negative in each half cycle. So these switches S1 and S2, they will have to carry both positive as well as negative current. So, but they only have to block positive voltage. So that is why the switches have to be voltage unidirectional and current bidirectional. So now we come to three-phase inverters. The simplest way is 180-degree conduction. So in each half bridge, the top switch is on for 180 degrees and then it is turned off, and at the same time we turn on the lower switch. So this is 180 degree, each switch is conducting. For the other legs, we will just phase shift these switching signals by 120 degrees. And for the C phase, we will switch phase shift them by 240 degrees. So that we get three-phase voltage. And then you can find out the line voltage between two lines by subtracting the VAN and VBN voltage, for example, for VAB. Similarly, you can do for other VBC and VCA. You will find that the shape is same, just that they are phase shifted by 120 degree or 240 degrees. And you can also find the RMS or the fundamental of this quasi-square waveform. It will be 0.78 times VDC. For 120 degree operation, in each phase leg half bridge, we top switch is first on for 120 degrees, then we wait for 60 degrees, and then we turn on the bottom switch for 120 degrees. So each switch is on for 120 degrees, and then for each half leg, for each leg or half bridge, there are two 60-degree intervals where no switch is on. And similar we do for the other phase legs, only phase shifted. And then you can find the load voltage waveform, whether line voltage or phase voltage. You just have to see which voltage comes across what portion. And if you see the RMS, it is less than 180 degree mode of operation. So the advantage here is that the conduction time is less, so we may get less conduction losses, but the disadvantage is that the output voltage is also less. So now we come to pulse width modulation. Why do we use pulse width modulation? Pulse width modulation basically means, so before we had the voltage was on for 180 degrees and then off for 180 degrees, or minus VDC for 180 degrees. Now we want to modulate. Modulate means change it according to some condition, change this voltage width. So instead of 180 degree width, now we want to have, let's say, less than that. So for some portion, we will get VDC, and for other portions, we will have zero voltage. So we are modulating the pulse, the width of this pulse. So what advantage do we get? The advantage here is that, for example, if we see the harmonics of this waveform, which is a quasi-square waveform instead of a square waveform, you will see that for some values of pulse width, 2D is the pulse width. For some values, the harmonics are reduced to 0. So if the pulse width was pi, if you see that at this point, all the harmonics are at their maximum value. So for example, the third harmonic, it starts from 0 to some maximum and then it goes to 0, then again to some maximum. And for pulse width is, if the pulse width is pi degrees, that is normal 180 degree operation, then the harmonics are maximum. But for other degrees, we can reduce the harmonics. So for example, for 120 degrees, the third harmonic is eliminated, it is 0. Similarly, for other values, we will get reduced different harmonics. So by varying the pulse width, some harmonics can be reduced or eliminated. So this was for one pulse, which is single pulse PWM or single pulse width modulation. Then we can have multiple pulse width modulations, in which instead of only one pulse per half cycle, we can have multiple pulses per half cycle. But in this case, as we saw in the questions also, that the pulse width will be constant and the spacing between two pulses will also be constant. And finally, we have sinusoidal pulse width modulation, in which the pulses will vary sinusoidally. So first we will have a small pulse duration, then it will increase, and then it will decrease to zero. Then we will get negative voltages. So this is the three types of options. And the modulation index is basically the peak of the carrier, sorry, the peak of the reference divided by the peak of the carrier. And by increasing this modulation index, we will get the output RMS will be increased. And the point here is that we can reduce harmonics by having more number of pulses or multi-pulse or increasing the switching frequency, but our switching losses will also increase. So there's a trade-off we have to make. So next we come to multi-level inverters. So up to now what we have studied is a two-level inverter, so that we can have either zero at the output or VDC at the output. Output of each phase leg can be 0 or VDC. But now, for example, here I have shown a three-level inverter. And here if you see that each capacitor has a voltage of VDC by 2. So we know that if we turn on the top switch, we will get VDC at the output, full VDC. And if we turn on the bottom switch, we will get 0 at the output. But now if we turn on the middle switch, we will get this, the lower capacitor voltage at the output, which is VDC by 2. So in this case, we have three levels at the output. So similarly, you can have multiple levels, more than three levels. In this kind of a system, we will require more switches and more capacitors. Why do we use multi-level? So for example, for a two-level inverter where we have 0 and positive, and then in the negative side, it's the same thing. If you see, we have a square wave or a quasi-square wave at the output, but we would ideally want a sinusoidal wave. And in this case, the error between what we desire and what we actually are getting is quite high, because we only have these two levels, 0 and the full VDC. However, if we had multiple levels, then we can more closely approximate the sine wave. And that means the harmonics in the current and voltage will reduce. And that will give us a better, lower THD, better quality waveform at the output. And another advantage is that the switch stress is also reduced. So, for example, in this case, when the middle switch is on, the voltage stress across the bottom device is VDC by 2 only. So in some cases, the voltage stress will also be reduced. So that will give us some advantages. We can reduce lower voltage devices, the RDS on, the conduction loss, switching loss, they will get also reduced. So that will have other advantages. But the disadvantage in this multi-level inverter is that we will require more number of switches and capacitors and components. And the complexity will also increase, because now we have to control all these devices. We have to ensure that the capacitor voltages are VDC by 2. So it will require more complex analysis and operation. So the first way how we do this multi-level converter is a diode clamped converter. In this case, for example, we have 4 switches in one leg. They are connected back to back or in series. And then we have 2 diodes that are connected to the midpoint of the capacitors, as well as to the switches midpoint of the top switches and the bottom switches. So if we require VDC voltage at the output, we will turn on S1, S2. And you can see the point A will come to the top of the bus. And the voltage across VA and the negative bus will be VDC. Now if we want 0 at the output, we will turn on S3 and S4. So that is easily understood. Now if we want VDC by 2 at the output, we will turn on S2 and S3. But only one of these will conduct at a time depending on the current direction. If the current direction is positive, it is flowing out of the terminal A into the load, then D1 and S2 will conduct. So you can see the current will flow positive. The diode can only allow positive current, and it will conduct from D1 to S2. So D2 and S3 will not conduct if the current is positive. If the current is negative, that means it is flowing into the A terminal, then S3 and D2 will conduct. Okay, so there are two options for the VDC by 2 voltage depending on the current direction. So someone is asking, in this case the output voltage is AC or DC. So if you're asking about this diode clamped or even the multi-level, so it depends on across which two points are you taking the voltage. For example, here I was taking the voltage across A and N, but actually we will not have the load across A and N. We will have the load across A and another half bridge B. So then we can have AC voltage. That means it will go positive as well as negative. Similarly, for 3-level, we will have more. We can have more legs, or whether it will be 3-phase, and then the voltage will be between different points. So there we can get positive as well as negative voltage. I was just showing for illustration that if we take these 2 points, A and the negative point, for this type of converter we will have 2 levels, and for the 3-level inverter we will have 3 levels, and then we can have multiple half bridges to get the actual AC voltage. So this was diode clamped. For the next one is a flying capacitor, in which we have again 4. So I am showing the 3-level case because that is the simplest multi-level. 2-level we have seen, so now we are seeing 3-level. For more than that, it will become more complex. So, but if you understand the concept of in the 3-level case, then you can understand it for the higher levels as well. So for flying capacitor, we have additional capacitor whose voltage is maintained VDC by 2. So this voltage we have to maintain as VDC by 2. So now let us see how we get the voltages. For example, VDC and 0, you can understand easily that by turning on the top 2 switches, we will get VDC between A and N. And by turning on the bottom 2, we will get 0 between A and N. And now if we want VDC by 2, we have 2 options. One option is just S2 and S4 we will turn on. Because if you see S2 and S4, then we will go through this middle capacitor. So we will get VDC by 2 at the output. But there is another option. We can turn on S1 and S3. And if you see, then in that case, we will get it will be VDC minus VDC by 2. So these 3 capacitor voltages come in such a manner. The polarity is such that we will get VDC minus VDC by 2. That means we get VDC by 2 at the output. So these multiplicities are used in the modulation of this kind of a converter to achieve some objectives. So this was the flying capacitor. The next one is the cascaded edge bridge, but I have not shown here because it is relatively easy to understand the basic concept. So lastly, we have the Z source inverter. So Z source inverter, there are different types of Z source inverters. Here I have shown a VSI based. That means there is a voltage source, and the switches will be just like the VSI switch. So it will be like an IGBT plus anti-parallel diode, or a MOSFET, or thyristor plus anti-parallel diode. So this is a VSI based Z source inverter. Between the DC voltage source and the inverter half bridges or inverter legs, we will have an impedance network. Hence it is called Z source or impedance source network. So this kind of a converter, it will provide us additional functionality compared to the VSI or CSI. So for example, VSI is a buck type of a converter. The output voltage will always be less than the input voltage, but we cannot get more than the input voltage using the VSI. So that is where the Z source inverter can be of use, because it will provide us a higher voltage. It can provide us a higher voltage. So here I've shown just a basic working. So first we talk about the normal state and a shoot through state. So the normal state is just like the normal functioning of the VSI. So in each half bridge, one switch can be on or no switch can be on in a half bridge. That is also can be a switching state. But in the VSI, we cannot have a switching state that is called a shoot-through switching state. That means S1 and S4 are both on. In each leg, the turning on two devices we cannot have. But we can have that in the Z source inverter, and that is called a shoot-through state. And that there will be the equivalent circuit will be different in these two states. For the normal state, we will have some load current and we will get some voltage at the input to the phase legs. So Vi, at the voltage Vi, we will get some voltage in the normal state. And if you see, the inductor voltage will be VDC minus VC. So for example, in this loop, you can see that the inductor voltage given this polarity, it will be VDC minus VC. And the Vi voltage will be VC minus VL. So VC minus VL. So if you see this loop, VC minus VL. And I can substitute from the earlier equation VL, I will get 2VC minus VDC. So in normal state, normal state is operated for some duration of time, T1, out of the entire switching cycle. So in this state, these are the inductor voltages and the input voltages, input to the three half phase legs. In the shoot through state, the Vi voltage is 0 because we are shorting using the phase legs, and the current will just flow between the impedance network through the shorter leg. So it will not flow through the source. In this case, if you see the KVL, that VL will be equal to VC. So through the shorter leg, VL will be equal to VC. In both cases, you will see that VL will be equal to VC and Vi is equal to 0. So now we have, and this shoot through state will be for some interval T0 out of the full interval. And T1 plus T0 time is equal to T time. So there are only these two options here. So now if we apply the volt second balance of the inductor for these two equations, we will find that the VC voltage is given by this equation, T1 divided by so actually I think it should be T1 minus T0 here in the denominator. It will most likely be T1 minus T0 in the denominator. So that is the VC. We can also find the Vi peak now. So now once we have VC voltage, which is the average value of the voltage across the capacitor, then we can find the Vi peak. And for the shoot through state, Vi is equal to 0. So Vi peak will be in the normal state, which is 2VC minus VD. And by substituting the value of VC, we will get that Vi is equal to this factor, T divided by T1 minus T0, which is B factor or boosting factor. And you will see that this factor is always greater than or equal to 1. Because T will always be greater than T1 minus T0. T1 minus T1 and T0 are both fractions of T. So T1 minus T0 will be also a fraction of T, and this whole thing will be always greater than 1. So basically Vi now is a voltage, or a peak voltage of Vi is greater than greater than the VDC voltage. So in the just like the normal VSI case, the AC voltage is given by modulation index times VI by 2. The peak of the AC voltage is given by this equation, and since here VI is equal to P VDC, so we get this equation for the AC output. So in that case, that means since B can be it is equal to or greater than 1, and M can be 0 to 1. So basically, using this multiplied factors M and B, we can get both buck as well as boost operation. So this is one application of Z-source inverter in this configuration. And the additional functionality that we get using this impedance network is buck boost functionality. Okay, so that was the summary of the lectures. The problems, if somebody needs any additional case, MB is the product of M is the modulation index, and B is the boosting factor, which we found in this equation. Because VI peak is equal to B VDC. So it is M into times B times VDC by 2. Okay, so this was the summary. If anybody has any doubts, you can ask for like 5 minutes. Other people who they can leave if they don't have any doubts. Okay, so the problem solving, this lecture is being recorded. It will be posted on YouTube. You can find the link. Okay, so thank you all for joining. So if anybody has any questions, you can ask. I will be here for 5-6 minutes.